breaking the universe. Hello, everybody. Welcome to ScienceTime, the podcast that explores scientific topics that aren't covered as much as I think they should be. I'm your host, Corbin, and today we're talking about quantum entanglement and how it could, quote-unquote, break the universe. Now, for anyone that doesn't understand concepts of quantum mechanics, do not worry. I'll be covering everything you need to know to understand this episode. So, what is quantum mechanics? Quantum mechanics is essentially how physics observes very, very small objects. Think about atoms, electrons, protons, etc., all the way down to the smallest unit of matter that we know of, quarks. You get quarks by smashing atoms into each other really fast, and they exist for a very short period of time. It's no longer than a nanosecond, maybe. Anyways, why is quantum mechanics different from normal physics? A general rule of thumb is the smaller things get, the less they follow normal conventional rules. Subatomically, of course. An example of this would be two objects colliding. Let's say two cars, for example. General physics says that their force will be distributed between the two objects and a crash will happen. However, if we scale those cars down to an atomic scale, a subatomic scale rather, the collision could do anything from creating light from the protons releasing energy to an atomic bomb explosion. Context does depend heavily, though, in this instance. So, why did I explain this? It's because the quantum mechanics relates heavily to how entanglement works, and how quantum mechanics laws are very different from the normal laws of physics. Now, I'll next explain what quantum entanglement is. Quantum entanglement is when two quantum particles interact with each other and become quote-unquote entangled. They are interdependent on one another, so if one is in a certain state, the other has to be in a certain state as well. Think about plants and animals. If plants die in the winter, then the state of the animals also reflects that. However, the strangeness about entanglement properties is what a lot of people like to call, quote, spooky action at a distance, which is not technically correct, but it does make sense. Essentially, what spooky action at a distance represents is the knowledge of interdependence. Let's say I have two shoes, the left one and the right one. If I put each of them in a separate container and throw them off of a cliff, I don't know which shoe is which. However, let's say that I go down to where the shoes are and open one of the boxes. Let's say that the box contains the right shoe, which means that the other box must contain the left shoe. However, the problem with this is that I only knew the left shoe was in the other box because I observed the right shoe. Let's scale this down to electrons. Electrons have a property where they spin either upward or downward. So if we have two of them are entangled, then if one of them is spinning upward, the other has to be spinning downward. Now let's go back to the shoebox metaphor, but replace them with electrons. If I observe its spin to be upward, then that means the other will have a downward spin. But if you know anything about physics, or anything about Schrodinger's principle, we know that if we observe a particle, its properties change. A popular example to understand this would be Schrodinger's cat. If you leave a cat in a box with poison, you don't know if the cat is dead or alive until you open the box, thus changing the property/state of the cat. Because you didn't know if the cat was alive or dead until you opened the box. Now, because of this entanglement property, it breaks the laws of conventional physics, which states that nothing can travel faster than light. However, using the power of observation, we can determine the state of the other electron faster than the speed of light. How is this? Well, let's say that two electrons were an infinite distance away from each other and they were in individual boxes. If we observed that one electron was spinning upward, we would know for a fact that the other electron is spinning downward simply based on the relation. But that isn't exactly what people call spooky action at distance, but it's just the result of them being together in a system. Spooky action at a distance represents the ability to copy one particle's behaviors onto another particle. Essentially, if I had two electrons, electron A and electron B, and they both had different properties such as an upward and downward spin, then if they were entangled, I could transmute the properties of an upward spin, aka electron A, onto electron B if they were entangled. This means that electron A would then transmute its properties onto B, making it essentially a copy of electron A. Teleportation quantum entanglement is more like transmutation or copying at a distance, but it happens instantly. Alright, now we are getting into the fun stuff and how quantum physics and entanglement break the universe. For this, we need to look at the first teleportation experiment. Chaoyang Liu and Hua Pan carried out the first experiment teleporting multiple degrees of freedom of a quantum particle in 2015, proving that teleportation, or quantum entanglement copying, is completely possible. Even though the distance was minimal, it was still teleportation, and from there, the science world went crazy. In 2017, China did another quantum entanglement experiment where they teleported photons over 1,400 kilometers in their satellite. So we're finally able to copy and paste quantum things. Cool, but what about the actual teleportation of us, human beings? Well, as we know, it's not actual teleportation, but for it to happen, we would need power. A lot of power. A study done by the University of Leicester states that to teleport a person and all of their data, it would take 2.6 times 10 to the 42nd bits of data. To transfer all of that data, it would take the power of the entire world, for the lifetimes of a few 100,000 universes. But that's with the power we have right now. Some scientists theorize that we could be able to teleport within as little as 100 years. That could maybe happen with black hole energy, which we'll get into in a bit, but for now, let's focus on one great idea and usage of quantum entanglement: computers. Computers have been around for some time now, but quantum computers have been theorized for a long time, and we're finally making strides to make this fiction a reality. And what these machines can do is incredible. How close are we, though? The general consensus is that roughly in the next coming decades we will have much more efficient quantum computers, and they might even become commercially available. A quote from Scientific America essentially states this. Quote, "If 10 years from now we have quantum computers that has a few thousand qubits, that would certainly change the world in the same way that the first microprocessor did. We and others have been saying it's just 10 years away." Unquote. Some people are scared of machines having that much power, though. The AI from quantum computers could far surpass the limit of human intelligence. And Google claims that their quantum computer is 100 million times faster than the normal conventional computer. And that isn't even close to the goal that they're trying to reach. So why would people be scared of these quantum computers? Well, with quantum computers, you could have artificial intelligence that far surpasses human intelligence. And this scares a lot of people because, movies like Terminator and books and Elon Musk all saying that, AI is probably going to be the death of the Earth. But if you take another approach to it, if you have an all-powerful, all-knowing being, or I guess intelligence, you could theoretically program it to be benevolent if you wanted it to be. And so I think that people really just forget that being evil is not a natural state. That's just my input on it. Anyways, let's get into black hole energy. Something that I brought up earlier. What is it, and how could we harness it? First, we need to explain the parts of a black hole. A black hole can be broken into 4 main important parts. Number 1, the singularity. This is the middle of the black hole, and this is where all the mass of the black hole is, or at least 99.999% of it, and it occupies very little volume. It almost has a volume of space equal to 0, and because it has such a little space and volume, it has an absolutely enormous gravitational pull. The next is the event horizon. This is the point where things could go wrong if you're too close to a black hole. This is essentially the, quote, no return point. Not even light can escape from here. The third is the accretion disk. This is the disk that's made up of a bunch of matter. It's spiraling towards the black hole, usually made up of stars and planets and such. The next is the ergosphere, the important one. If a black hole is spinning, then that means that the space-time around the black hole is also spinning. And this is what the ergosphere basically is. So, now that we have all the important parts of a black hole, let's get into how we could harness the energy from one. If you wanted the most efficient process for getting energy from a black hole, you'd need to do what's called creating a black hole bomb, and we'll get to that in a tiny bit. Since we can get up to around 40% of a mass's energy using a rotating black hole, this is absolutely astronomical for humanity. The equation for energy, of course, and we all know this, is E equals mc squared. What you might not know is what it actually means, which this equation means the energy of a system is equal to the mass of something multiplied by the speed of light, 3 times 10 to the 8th meters per second squared. So that's a lot of energy. Unfortunately, we can only harness around 40% of this energy with a black hole, but this does mean that a 1 kilogram object can obtain 35.96 petajoules of energy, while a nuclear bomb, a 1091 kilogram nuclear bomb, only creates around 5 petajoules. This means that on average per kilogram, a nuclear bomb releases 0.00458 petajoules per kilogram, making a black hole around 7,500 times stronger than a nuclear bomb. How much energy is in a single joule, though? A single joule of energy is equal to moving a 1 kilogram object 1 meter. A petajoule is 1 quadrillion joules, or 1 times 10 to the 15th joules. It's a lot of energy, and that's off of a single kilogram. We almost get 36 of these whenever using a black hole. That would be the same as moving a 1 kilogram object 36 quadrillion meters. If we use the speed of light, that would take you roughly 4 light years. But what if you wanted even more energy? How you would do this is basically done by creating a black hole shell. You would have to make a mirror so big that it surrounds the black hole. Then you could shine either a beam of electromagnetic waves into it or light into it. Essentially, some of the light would go straight into the black hole past the event horizon, but most of the light would bounce off the mirrors and gain exponentially more energy. If you didn't let this light out, it would cause a supernova explosion. But if you could get the light out in a constant stream, then you could have near limitless energy for trillions of years. Now, unfortunately, we aren't exactly close to making this a reality in the near future. But it is a very likely possibility for the distant future whenever humanity conquers the stars. It's exciting to think about all the possibilities, from black hole energy to AI that could rule the world benevolently, or evil. Anyways, if you enjoyed today's episode, please leave a like. Maybe recommend it to someone who would enjoy listening to these types of podcasts. Sorry that this was a relatively short one, but anyways, that's just about all I have to say. Thanks for everyone who listened to this, and I hope to see you guys next week. See ya.